All right, let's talk about the magic behind modern AI. You've heard the words, right? Neural networks, deep learning, GANs. They could sound pretty complex, almost like something out of a movie. But really, they're the engines driving the AI that's changing everything around us. So what are they, really? In this explainer, we're going to peel back the layers and get to the heart of the architectures that make AI tick, from the absolute basics to the really creative stuff, and even the big challenges that every single developer runs into. Let's get right to it.
I mean, you see the results of these architectures everywhere you look. Just think about what's going on inside a self-driving car. It has to see and understand this chaotic, constantly changing world in real time. We're talking about spotting cars, people, street signs, lane lines, all while trying to predict what everything is going to do next and making critical decisions, in a fraction of a second. This isn't just a future concept anymore. This is happening right now thanks to modern AI.
And then you look at a field like medicine, and the stakes get even higher. We have systems now that are trained on millions of medical scans, learning to find those tiny, subtle little signs of disease that might even be missed by a human expert. We're actually talking about AI models that can spot certain cancers earlier and more accurately than a whole team of trained doctors. It's just incredible.
Or think about the AI that's becoming part of our everyday lives. An assistant that doesn't just hear your command, but can actually pick up the phone and have a completely natural conversation with another person to book a haircut for you or get you a table at a restaurant. The level of complexity there is just mind-boggling. So the big question is, how on earth does any of this stuff actually work?
Well, the secret is this massive shift in how we think about building software. For decades, programming, what we could call Software 1.0, was all about a human writing super detailed, explicit rules. If this happens, then do that. But think about a problem like recognizing a cat in a photo. How many rules would you even need? You'd have to account for the lighting, the angle, every single breed. It's basically an infinite list. So the whole idea got flipped on its head. With machine learning, or Software 2.0, we don't write the rules anymore. Instead, we just give the computer a ton of examples. We show it thousands of pictures of cats, tell it this is a cat, and we let the machine figure out the rules for itself.
So here's how we're going to break it all down. First, we're going to dig a little deeper into this whole new programming model. Then, we'll take a tour of the real workhorses of AI, the different kinds of neural networks. After that, we'll see what happens when AI starts to get creative. Then we have to talk about a huge challenge everyone faces, what I call the Goldilocks problem. And finally, we'll wrap up by looking at what the future of all this learning might hold. Okay, first up, let's really get our heads around this foundational idea, because honestly, understanding this Software 2.0 concept is the key. It unlocks everything else. It's not just a different kind of code, it's a completely different way of building things. And this diagram does a great job of showing what I mean. Imagine this big circle is the entire universe of every possible program you could ever write to solve a problem. In the old world, Software 1.0, a human programmer has to search through that massive space and find one single perfect point, the one program that gets the job done. But with Software 2.0, our job totally changes. We don't have to find that exact point. Instead, we just set a goal, like get really good at spotting cats, and then we let an algorithm search a whole region of this space, using data to automatically find a program that works. It's like we've gone from being an architect who has to draw every single line of a blueprint to being a guide who just points at a mountain and says, get to the top. And as AI researcher Andrej Karpathy says so well, this whole shift really happened because it had to. For so many of these messy, real-world problems, it is just way, way easier to collect a ton of data than to try and write down all the rules. Think about it. Could you write a program that describes the sound of a bird singing? It'd be almost impossible. But you could easily record thousands of bird songs. And that, right there, is the power of this new way of thinking. Okay, so now we get the why. Let's get into the how. The engine that makes this whole Software 2.0 thing go is the neural network. But here's the thing. It's not just one thing. It's more like a whole family of specialized tools, and each one is designed for a very specific kind of job.
Let's start with the classic, the original, the artificial neural network, or ANN. You can think of this as the all-arounder, the generalist. It's amazing for working with structured data, the kind of stuff you'd find in a spreadsheet, like financial data or customer info. Information just flows straight through. It comes in an input layer, goes through these hidden layers in the middle where all the processing happens, and then comes out the output layer with an answer.
So what's actually going on inside these layers? Well, it all comes down to this one simple unit, a perceptron, or you can just call it an artificial neuron. Think of it like a tiny little decision maker. As you see here, it takes in a few different inputs: Then, for each input, it decides how important it is. That's the weight. Finally, based on all that weighted information, a little thing called an activation function decides if the neuron should fire and send a signal on to the next layer. And really, the whole magic of learning is just the network tweaking millions of these little weights, these little importance knobs, until it gets the right answer over and over again. And we build these powerful networks just by stacking these simple neurons into layers. The first layer gets the raw data. Then you have one or more hidden layers that transform that data, with each layer learning to spot more and more complex patterns. And finally, the output layer gives you the result. And when you hear the term deep neural network, that just means it has a lot of hidden layers, which lets it learn incredibly complex stuff.
All right, time for our first specialist, the convolutional neural network, or CNN. If the ANN is the generalist, the CNN is the vision expert. It's specifically built to understand data that's laid out in a grid, which makes it absolutely perfect for images. Its secret sauce is something called a convolutional layer, which acts like a whole bunch of little filters that slide over the image, automatically learning to spot important features.
You know, the coolest thing about how CNNs learn is that it's hierarchical, kind of like how our own brains process vision. Just look at this. The first layers in the network, they learn to see really simple things, like basic edges or corners or little blobs of color. Then, the next layers take those simple pieces and learn how to combine them into more complex things, like textures or an eye or a tire on a car. And then the final layers put all those parts together to recognize whole objects. The network literally teaches itself how to see, from the ground up.
And here you can see that exact process in action. The image of the car goes into the network on the left, and you could just watch as it moves through the layers. Each layer lights up as its feature detectors spot more and more complex patterns. It goes from lines and curves to textures, wheels, and windows, until that final layer spits out the answer with confidence: car. So our next specialist is the recurrent neural network, or RNN. And here's the perfect way to think about it. If CNNs are masters of space, RNNs are masters of time and sequence. They're built for data where the order of things matters, like the words in a sentence or stock prices over time. Their secret is this little loop, where the output from one step gets fed back in as an input for the next step. This simple trick creates a kind of memory, which lets the network understand context. So just to quickly recap that tour, this table puts it all together nicely. You've got your ANN, the go-to for structured spreadsheet-like data. You've got your CNN, the vision expert that automatically finds features in images. And then you have the RNN, your sequence specialist, with its memory for things like language and time. Each one is a specific tool for a specific job.
Okay, so we've seen how AI can understand the world. It can classify things, it can recognize patterns. But what happens when we ask it to create something totally new? This is where things get really, really interesting. We're talking about a genius architecture called a Generative Adversarial Network, or GAN.
The idea behind a GAN is just so clever. Instead of one network, you have two, and you pit them against each other in a competition. The first one is the generator. Its job is to be like a master art forger. It tries to create fake data, like a picture of a person who doesn't actually exist that looks totally real. Then you have its opponent, the discriminator. It's like an expert art critic. Its only job is to look at an image and decide if it's a real photo or a fake one made by the generator.
And this constant battle is exactly how they both get so good. The generator makes a fake, the discriminator judges it. That judgment, real or fake, gets sent back as feedback. So if the discriminator catches the fake, the generator learns it has to do a better job. But if the generator actually fools the discriminator, well, then the discriminator learns it has to get smarter. They go back and forth thousands, millions of times, each one forcing the other to get better, until the generator is creating fakes that are just impossible to tell from the real thing.
Okay, so no matter what kind of model you're building, whether it's a simple one or a crazy complex GAN, there's this one fundamental problem you always have to deal with. It's officially called the bias-variance trade-off, but I think a much better name for it is the Goldilocks problem.
So this trade-off is a balancing act between two kinds of mistakes. On one hand, you have bias. A high bias model is way too simple. It makes big assumptions and just misses the real pattern in the data. We call that underfitting. On the other hand, you have variance. A high variance model is way too complex. It's so flexible that it doesn't just learn the real pattern, it also memorizes all the random noise in the data. We call that overfitting. And the goal is always to find that perfect model right in the middle, the one that's just right.
Let's make this super clear. So here we have some data points, and they clearly follow a nice curve. This red line is our first try, a really simple model. It has high bias. It's just too simple. It's too rigid. It completely fails to capture the real shape of the data. This porridge is too cold.
Now check out this blue curve. This model is a bit more complex, but not too complex. It has enough wiggle room to follow the general curve of the data, but it doesn't get sidetracked by every single little random dot. It's found the real pattern. This porridge is just right.
And finally, here's the green line. This is a super powerful high-variance model. It's so flexible that it twists and turns and tries to hit every single data point perfectly. It's basically memorized the noise right along with the signal. Now, it would get a perfect score on this data, but the moment you showed it new data, it would completely fall apart. This porridge is too hot. And this, right here, is the constant balancing act that AI developers are always playing.
So we've gone through the big paradigm shift in programming, we've toured the different neural networks, we've seen how AI can get creative with GANs, and we've talked about the universal Goldilocks problem. So let's put it all together.
So I think the main thing to take away from all this is that these architectures don't live in their own little bubbles. A real AI system, like that self-driving car we started with, is like a symphony of all these different parts working together. It's definitely using CNNs to see the road, but it's probably also using RNNs to predict where a person walking is going to go next. You might even have GANs generating new, tricky driving scenarios to train the car on. And underneath all of it, for every single component, you've got that constant, delicate balancing act of the Goldilocks problem. These aren't just algorithms, you see. They're a whole new way of solving some of the world's most difficult problems.
And that leaves us with one last really fascinating thought. For a long, long time, the bias-variance trade-off has been like a fundamental law of machine learning. But now, with these absolutely massive models, models with billions or even trillions of parameters, we're starting to see something weird. These giant models can be trained to the point where they perfectly memorize all the training data. Now, that should mean they have insanely high variance and should be terrible on new data. But a lot of the time, they work brilliantly. This strange effect suggests that at a certain massive scale, our old rules might just start to break down. So the question I'll leave you with is this. Are we walking into a new era of AI where, against all logic, more and more complexity actually makes models better at generalizing? And if so, what does that really mean for the future?